So this is the first video for chapter 3. We're going to cover section 3.1 in this first video. So pause, copy down this panel, and then I'll start generating out. Right. So chapter 3 introduces one of the fundamental themes of this course, which is hypothesis testing. We're going to make conjectures, we're going to gather data, and we're going to look at the data and see whether it supports our hypothesis or not. So we need to be able to test the hypothesis. And in this chapter, the way we're going to test hypotheses is by one specific method called a permutation test. And we'll develop other tests for hypotheses in other chapters. All right. So in general, with a hypothesis test, we seek to determine whether a given factor, and in this case, it'll be a categorical factor, we seek to determine whether a given factor, categorical variable, we seek to determine whether a given factor or categorical variable impacts an outcome, or if the observed outcome probably occurred by chance, right? Now note there's some quotes around outcome and probably, so we have to define those words better, which we'll do throughout this video in the next few. Okay. All right, so here's an example. You got 6 mice, you're gonna run them through a maze one at a time, you're gonna time each mice to see how long it takes them to get through the maze. But 3 of the mice have received a drug prior to the running, and they're going to be given the label D for drug, and the other 3 mice have not received the drug, so they're going to be given the label C for control, okay? And the question might be, does the drug impact how well they run through the maze? So we give drugs to 3 mice, no drugs to the other 3 mice, one at a time, we run them through the maze and we time them, and here's our data over here. So each mouse has a number 1 through 6. The first 3 mice got the drug, and then the 4, 5, and 6 did not get the drug. It didn't line that up too well. But 4 is a control, 5 is a control, 6 is a control, and there's their times, okay? And so one way I could ask, well, did the drug slow down the mice, is I could take the average of the mice that received the drug, the average of their times, which was 25 seconds, and compare it to the average of the control group's times. So those are the 3 times of the control mice divided by 3, and I get 20.3. And I can look at the difference between those 2 averages, and I see that I get an observed value of 4.6 repeating seconds. And so you might say, well, hey, that looks kind of significant. Looks like the drug probably slowed the mice down, okay? But just looking at 3 mice in each category and taking a difference isn't necessarily the best statistical test we can do. So let's see how we might improve upon this. All right, so after I'm done futzing, why don't you copy down this, pause it, copy down this panel, and I'll churn around. All right, so we're going to test this question, this hypothesis that the drug appears to make the mice slower running through the maze. And the reason we should be skeptical about just seeing that 4.6 seconds is it's possible this time difference simply occurred by chance. I mean, maybe we just happen to inject 3 of the slower mice with this drug, and what we're actually seeing is that they're just slow mice and the drug's not doing anything. Okay? So the way we're going to test it via permutation test is we're going to simply take the 6 mice and randomly assign 3 of them to be in the D category, independent of whether they got the drug or not. So remember, mice number 1, 2, and 3 actually got the drug. Mice 4, 5, and 6 did not. But if I just take those categories of D or C and just sort of randomly assign them to these mice, let's see what happens, okay? So here's my 6 mice again, and I've not changed their ID number. The first 3 are the mice that actually got the drug, the next 3 are the ones that did not. But let me just mess up those categories. Let me permute the D's and the C's there, okay? So now I'm gonna say mouse 1, 4, and 6 are in the D group, and mouse 2, 3, and 5 are in the C group. Same times as before, okay? I didn't run the mice through the maze again. I just used their existing times and permuted the D's and the C's, okay? And now let's calculate the D average and the C average. So the D average, that'd be the average of 30, 18, and 22, and the C average would be the average of 25, 20, and 21. And I take the difference and I get 1.3 bar seconds. So here's another way of just saying, look, by chance, 3 of these mouse are considered Ds, the other 3 are considered Cs, and I see a difference of 1.3 bar seconds, okay? So that's one permutation of the Ds and the Cs. It turns out if there's 6 mice, I can pick 3 of them to be D mice in 20 different ways. So there's actually 20 different permutations of the Ds and Cs. So there's 20 different ways to select 3 mice to be D and the rest to be C. And for each of these 20 permutations, let's calculate and record this difference, the average of the new Ds minus the average of the new Cs, okay? And the book actually does that in the table on page 51. Okay, so it's in your book. You can look it over, and right in the far column is all those differences of the averages. Okay, and one of those permutations happens to be the actual correct assigning of D and C based on whether the mouse received a drug or not. Okay? All right, and if you look on that table, you'll note that 3 of those 20 permutations yielded differences, diff values of at least 4.6 bar seconds. So if I look it over, there's one of 4.67 seconds exactly. That's the one we started with. There's another one randomly assigned that gave us a difference of 5.33, and another that gave us a difference of 6.00 seconds, okay? So 3 out of the 20 times, just by random chance, we see a diff value that's as big or larger than the diff value we observed when D meant drug and C meant control. So then you have to ask yourself the question, well, if 15% of the time the difference that I saw can be matched or exceeded just randomly, was it really the drug that was making the difference, or was it just random chance that perhaps better explains it? All right, and we'll discuss how we should decide that question in future videos.